On the first run we saw it and we weren't sure what we were looking at.
Valeska was mentioning that these results were extraordinary if they're true. I said, well, let's wait and see.
These serendipitous moments don't come often in science, and it could have very far-reaching implications for the hydrogen storage societies. The reason that everyone's excited about hydrogen is because we're running out of fossil fuels, obviously. And hydrogen is, well, it's been touted as a green, renewable energy source.
It's readily available. There's lots of it about, albeit tied up in water or biomass. So it's easy to produce in principle. You can store it, although there are technical challenges there. And you can use it in a variety of different devices at the end to produce energy in fuel cells or in combustion engines.
But the problem is it's a gas at room temperatures and pressures, so it takes up a lot of room.
Let's imagine you need to drive a car, say 300 miles, on an engine powered entirely by hydrogen. You would need probably around about 5 kilograms of hydrogen, which is about a third of the weight, or third of the mass, strictly, that you need for gasoline or diesel. However, the volume occupied by this amount of gas at room temperature and pressure, where we are now, is about 60 cubic metres.
So if you were going to drive your car and fill up your tank with hydrogen, the fuel tank would be bigger than the car.
There are established technologies for storing hydrogen. One of them is liquefaction, basically cooling hydrogen down to only a few degrees above absolute zero. The problem there is you need a lot of energy to get it down to those temperatures, and then you need a lot of energy to keep it there. Another way is high pressure gas, which is storing it under pressures up to 700 bar. That's 350 times the pressure in your car tyre. So what we're trying to do is to develop technologies that rather try and raise the temperature above liquid hydrogen temperatures and drop the pressure compared to high pressure gas.
The work that we're doing at the moment is on solid state hydrogen storage. So taking a solid material with very small pores in it.
These pores are maybe only 5 or 10 atom diameters across, and it just so happens that these spaces are ideal to pack hydrogen molecules in.
It's like a solid state sponge. So we're making these materials with very small holes so that they can absorb the hydrogen onto the surfaces.
And I think it's still at the boundaries of our knowledge and understanding of what's going on. But my simple picture is this. The way that the hydrogen fits into pores, first of all, it sticks on the pore wall. It sticks on these surfaces inside the material and then starts to sort of pile up. But that piling up is limited by the proximity or the opposite pore wall, rather as if these two walls of the pore sort of force the molecules to pack, rather like billiard balls in a container. They all tend to pack in the most cost-effective or space-effective way.
These here are some of the samples that we use. So this one's a nanoporous carbon. These ones are two examples of metal organic frameworks. In this moth, it has chromium in it, and that's why it's green. And over here, this yellow one has indium in it. The thing is that the pores inside this are so small that you can't even see them. What we typically do in this lab is to measure the surface areas and hydrogen storage capacities of a lot of different materials. You see this tiny amount of the metal organic framework. It can store enough hydrogen gas to fill a beaker like this. So it's really compressing down the hydrogen into a very small volume. The hydrogen is coming from a gas bottle, which is the big red one over there. And then it goes into a dosing volume in our machine, and then it gets dumped into our sample volume. What this machine does is it measures the surface area of your materials and also the amount of hydrogen that you can store in your nano sponges. The measurements that we do here tell us a bit about the structure of the material that we're studying, but it doesn't tell us very much about the phase of the hydrogen that's inside the pores. Like, is it as dense as a liquid? Is it as dense as a solid? Where is it sitting in the pore? We don't have any sort of information like that. So that's why we had to go to the Rutherford Appleton Laboratories, to the ISIS facility, to use some neutrons. Neutrons are amazing for being able to penetrate matter, so you can look at really big samples, and you can also look at samples under pressure in stainless steel cans, and the neutrons will pass straight through and go and interact with your sample. Our experiments at ISIS were to do with having a sample, so we used a reference sample of an activated carbon. and we were dosing hydrogen in at high pressures and low temperatures to see if we could get any information on what the hydrogen was doing inside the pores. Well, the exciting bit about these results is this little peak here that's growing with increasing pressure. In a system where you've got hydrogen that's above its critical point of 33 Kelvin, it should never condense down to a solid phase or a liquid phase. But that peak is indicative of a condensed phase that has a density similar to solid hydrogen. So it's saying that we have compressed the hydrogen so much in the tiny pores that it's as if we have solid hydrogen in there. And that's something we never would have expected, like not at 77 Kelvin.
You never quite know how fundamental knowledge and understanding of a particular system may eventually translate into something that you or I might see on the streets or on the roads. You have to understand something at a basic molecular level before you can start to guess and predict what might happen when you use a material, if you like, in the real world.
Yes, this is kind of a big deal because all of the evaluation of hydrogen storage materials involves guessing the density of the gas inside the pores. Now that we have some sort of direct information on how the hydrogen is layering inside the pores and how it's condensing, then we can change our models so that we can evaluate which are the best storage materials. The experiments at ISIS are 24-hour experiments. So you need to bring a team with you and they need to be dedicated, so you've got shifts. So you might be waking up at 2 in the morning to twiddle something on the experiment. You also need to keep watching the data as it's coming off, because if you need to change something on the experiment, you need to do it when the instrument scientist is there. So our experiment in this case was 7 days, and so for that 7 days, we're concentrating on just this one experiment.
I was at the University of Edinburgh on a commitment there, and I was sending emails and texts to Valeska saying how things are going, you okay? And daily, the emails got more and more excitable, and I was getting excited. Valeska was mentioning that these results were extraordinary if they're true. I said, well, let's wait and see. And we have a colleague, Timmy Ramirez-Cuesta at STFC, who's been helping us on the beamline. And he was saying, this is extraordinary, this is extraordinary. And so we were getting more and more excited. And I was doing this almost remotely by email, which is frustrating for me, but incredibly stimulating. You go to bed thinking, goodness, if this is right, this is going to go places. I
really like the idea that we're finding out new things about our system. And so I found it pretty exciting. The thing with this anomalous spike that we weren't expecting to see. So each run takes 12 hours to collect. On the first run we saw it and we weren't sure what we were looking at. And so at the second pressure it was still there and it just kept getting stronger and stronger. And then by about the third pressure we were starting to get quite excited because it was obvious that it wasn't an artifact of the experiment or the setup, and that it was a real peak that we were seeing. We're getting a paper together for a high-impact journal, so we're going to try and get the results out there as quickly as possible.
Knowledge and understanding about how the world works is absolutely vital in order to be able to predict, in order to be able to design, in order to be able to work better with materials and energy. So I don't know whether we'll change the world. I hope we'll make a contribution to a more sustainable world.